What the heck?
Good morning, everyone. Welcome to this week's eRefCom webinar. We're glad that you can join us today. I have a couple of things that I need to go over with you before I turn the presentation over to our speaker. Our antitrust disclaimer: we will not be talking about money or projects or contracts, no specifics. We ask that you do keep your mic on mute. If you would like to make a comment or ask a question during the Q&A, you're welcome to unmute yourself or raise your hand. We will not be using the chat function in Zoom today. We will be running everything through Slido. You can sign in with slido.com. The code for the session is RefCom, or you can use this QR code I'm showing on the screen. With that, I'd like to turn it over to John with Aspen Aerogels.
Hello, everyone. I presume you can see my slide here. Today's webinar topic is better DCU performance through smarter insulation design. My name is John Williams. I'm the Vice President of Marketing and Technical Services at Aspen Aerogels. I am a aerospace engineer by training, but I've been in the oil and gas business for about 16 years. 12 of those years, I've been paying particular attention to delayed cokers, and so that's what I'd like to talk about today. The agenda for today's discussion, I'd like to start by giving you a little bit of an insight as to why delayed cokers are so difficult to insulate. A little bit of inside baseball from the point of view of an insulator, from the point of view of an insulation manufacturer, and what it is that makes your particular unit so special. I'll talk a little bit about our product, the product that we formulated specifically for delayed cokers, and that is Pyrogel HPS. And then the meat of today's conversation is going to be around insulation and how it enters into delayed coker units at different phases in the life cycle. So we've kind of experienced all of these phases, whether we've come into a unit during maintenance and kind of routine operations or MRO, whether we are doing re-insulation on existing drums, or whether we're coming into a brand new greenfield unit or insulating new drums into an existing structure. Finally, we'll finish up with a facilitated Q&A via Slido, as Becky mentioned. So, why is it that DCUs are so difficult to insulate? Your business is operating a delayed coker unit. Our business is insulating lots of things. And in the 20 years that we've been in business, we've seen aerogels go from the bottom of the ocean to the surface of Mars, into nuclear reactors, rocket engines, fighter jets, the most ungodly fire scenarios you've ever seen. And in all of that time, I would argue that the hardest thing that we've ever had to do is insulate a delayed coker. What you ask is not a small thing. There is something particularly pathological about the way delayed cokers operate with respect to the insulation. And that's really because insulation has three things that kill it: heat, water, and mechanical abuse. And delayed coker has all three simultaneously. Heat, you can see here in the chart in front of you, basically have plotted the temperature profile through the insulation for really the two primary phases of coking operation. That is the coking itself, or the filling of the drum, and then the cutting operations, the quenching, etc. We drop the temperature to remove the coke from the drum. That temperature profile will cycle up and down at whatever cadence your unit operates. And so that cyclic temperature produces a lot of mechanical movement in the drum, up, down, in, out, even banana modes and other kinds of strange shapes and bulges and weird things that happen over time. So that's certainly hard enough. is all of the mechanical movement on a coke drum. The temperatures itself, in particular during the coking period, are high enough that it tends to burn out any organic materials inside the insulation. So your binder content and your mineral wool tends to go away on the inner few inches. And then finally, water. You have plenty of water every day because of your cutting operation, not to mention precipitation, weather patterns, etc. A lot of people assume that in a device that operates at 450, 500 degrees Celsius, that water would be the least of your concerns. But in fact, water can quite happily live inside insulation at very, very high temperatures, because the temperature through the insulation is a gradient. Sure, the inside is at a very high temperature during coking operations, but the outside is cool enough for liquid water to reside there quite happily. And then, of course, when we go into a cutting operation, it collapses towards the interior, and so you have this movement in and out of water, all of which tends to result in a rapid insulation failure. Because when insulation gets wet, it gets heavy. When insulation gets heavy, it sags, and when it sags, it tends to open up seams. These things are visually obvious in most of the cokers that we've had the pleasure of working in and around. You tend to see seams opening up over the years as the insulation gets heavy. The effect of that from our work is that generally you'll see that within 3 to 5 years of commissioning a new unit, the heat loss from the drums has generally gone up by a factor of 2 to maybe even 4x. And this happens largely because of sag. So in the infrared picture on the right, you can see that if you look at your drums in infrared, and if they've been in service for a number of years, you'll typically see concentric rings of heat, basically these bright spots, these rings. And what is happening there is that immediately above each of those hot spots is an insulation support ring. So that support ring is providing support for everything above it. And generally that comes in, say, a 10-foot bay. Within that 10-foot bay, as you add water and heat and mechanical abuse, eventually the insulation tends to settle, and it opens up a gap at the top of each bay, and it shows up as a concentric ring of higher temperatures. So that extra square footage, that square meterage that is basically bare steel radiating to the universe, will essentially produce heat loss that again is 2 to 4 times higher than it was originally designed for. So delayed cokers are very difficult to insulate, but simultaneously they're also very, very sensitive to insulation failure. It's basically a known factor in the DCU world that a 10-degree Fahrenheit drop in drum outlet temperature will cut your liquid hydrocarbon production by 1%. That means it'll shift your yield away from liquids, away from diesel, and towards solid coke, which of course is worth a whole lot less than your liquids. And we can plot this. We can actually look at this on a chart and see what the financial impact of that is. So the chart that you have in front of you, I've plotted the insulation R value. Essentially, it's a metric of insulation goodness or health or quality. And I've taken an example here of a 2-drum DCU processing 11,000 barrels per day, and with a baseline insulation design of 5 inches of mineral wool. So on day 1, everything's good. But over the course of a few years, as the heat and the water and the mechanical abuse starts to break down the insulation, it starts to slide off of this curve. This yield curve will drop to a thermal resistance that is a third or a quarter of what it was on the day that it was installed. In this particular example, the consequences of that drop are almost a $2 million a year shift away from liquid hydrocarbons and toward solid coke. This happens slowly, right? So this happens over the course of several years. If it happened between Tuesday and Wednesday, you would notice it immediately in your process data. But because the degradation is slow, it's hard to actually see it. You can visually see the impact on the drums. You can, in infrared, you can see it, the impact on the drums. But the fact is that impact has a financial component, and that financial component is large. So, punchline here is that what you do is difficult. It is uniquely punishing to insulation, and yet extraordinarily sensitive to insulation failure. That's why we developed Pyrogel HPS. Historically, in the delayed coker market, and really in the broader market for high temperature insulation, you really had two primary choices. There's mineral wool and there's calcium silicate. Most drums are insulated with mineral wool. It's a fine product, but in this particular threat environment, it does have its challenges, right? So it's a rigid material held together with adhesives. Those adhesives are organic in nature and they burn out at high temperatures. It also gets wet, and that wet contributes to a doubling or a tripling of the weight and therefore the mechanical sag that we see in those infrared pictures. Calcium silicate doesn't have binders to burn out, but it is basically a rigid cementitious block, and so it is subject to brittle fracture. All of that mechanical movement does over time basically turn it to rubble, and it has the same issues with water. Pyrogel HPS was designed from the ground up for delayed cokers. So this is basically a glass reinforced aerogel blanket material. It's a flexible blanket material, so it doesn't have any of the mechanical failure modes of a rigid block. And it's also extraordinarily thin. it has the best K value on Earth. And so as a result, Pyrogel HPS can reduce your thicknesses by 60, 70% in the same kind of service. It is also about 1/3 to 2/3 lighter by virtue of being so thin. So HPS, the requirement that we gave our R&D folks is that we needed to be exceptionally thin. We needed to be exceptionally tough because we do plan to reuse it even after exposure to high temperatures. And we needed to be extraordinarily resistant to liquid water. So thin, tough, and dry is what we produce. This is the finest product that we've ever made at Aspen Aerogels. So with respect to your life cycle that you encounter in your DCUs, I've kind of broken it up into 3 different sections. So there's really maintenance. Maintenance is where we generally get introduced into a facility. There's 120 some odd DCUs on Earth at this point. After 12 years of work in this field, we're in about 1/3 of them. And often, our first introduction into a delayed coker facility is on the feed lines and the overhead vapor lines. For whatever reason, delayed cokers are extraordinarily sensitive to feed line insulation performance, because generally when you have underperformance on the feed lines, it results in premature coking. Premature coking results in a whole lot of pigging, and pigging is basically lost production time. So I'm going to go through a case study in which we talk about how Pyrogel HPS can improve the quality of your feed lines and improve the profit of your unit. Then, of course, there's emergency repairs. You know, the material, it's fast to install. It basically comes in a roll. It's easy to basically slap onto a piece of steel and basically bandage things to keep it going. And then finally, mechanical clashes, right? Being 60 or 70% thinner than anything else means that we're going to fit where nothing else will. Where we typically see that being expressed is around the delta valves, where space is at a premium, around the nuclear gauges, where you have to try very, very hard to protect those things because they are expensive and sensitive to overtemping. And then just generally around clashes with structure and platforms. So my first case study here. This is a unit in the Midwest of the US. In this particular case, this process engineer actually gave us a quote stating that after reinsulating the feed line with HPS, they were able to drop the duty rate on the furnace, and they were also able to increase the time between pigging from weeks to months. By their calculations, that saved them $600,000 a year just by re-insulating the feed line. So with that kind of money on the table, I understand why this is often our first foray into a new delayed coker unit. As far as emergency repair goes, this is one of my favorite stories. And actually, this is the very first delayed coker in which we were installed in any significant way. This is actually a refinery on the US Gulf Coast. Back in 2008, it was hit by a Category 4 hurricane, and that hurricane stripped the coke drums bare. All of the insulation was torn off of it. And because of the way this particular unit operates, they were limping along at about 30% production until they could restart the DCU. They needed something very quick to get themselves back up and running. So basically they decided they'd been playing with Pyrogel for the last few years on piping and small pieces of equipment. They had some laying around. They just decided to put 30 millimeters or 3 layers on the drums. They did not even bother jacketing it. They just held it in place with chicken wire, restarted the drums, restarted the entire refinery. Apparently it worked well, because 10 years later, that temporary Pyrogel was still there. They had had no issues with it, despite the fact that it was not protected from the weather. There was no metal jacketing on that insulation. Over the last couple of years, they have been replacing those drums, and so now they have been re-insulated with a more permanent insulation system, which not surprisingly is Pyrogel, but this time covered with metal jacketing. Now, we don't recommend that you leave your Pyrogel unjacketed, but in the event that you have to, you're forced by circumstances on the ground, the material can survive. Okay, so having introduced ourselves to the maintenance side of a delayed coker, often the next step is to talk about re-insulation, like a more comprehensive usage to re-insulate the drums and basically upgrade their performance. This raises two interesting possibilities, and I'm going to share a case study for each one. The first possibility is this idea of super insulating. You have a certain amount of space, a certain space claim around your existing drums for the insulation that you have right now. And that's typically between, say, 4 and 6 inches, 100 to 150 millimeters. So that's the space that we have to play with. Having Pyrogel HPS, that you can fit more insulation power or R value into that same space, means that you can get a higher level of thermal performance. As we discussed before, each 10-degree increase in vapor line temperature will increase the gas and distillate production by 1%. And so if we did that, what would that pay for in terms of a thermal insulation system? The other option, which is, as far as I understand, completely unique to Pyrogel, is that in many cases, we can do insulation work while the drum is in service. We have done this twice, actually, completely re-insulated the shell of a delayed coker drum while the unit was in service. So I'll describe a case study around that here in a second. So returning to our yield curve, last time we were falling off to the left as our insulation was failing, but if we turn the dial in the other direction, what if we achieved more insulating power within the same 125 millimeter space? What would that achieve? Well, it's the same logic. As we move the dial to the right, all the way out to 5 inches, each time we tick it up by a notch of 10 millimeters, we're able to achieve greater liquid yield. Greater liquid yield gives us a higher margin. That higher margin helps us pay for the more insulation. And so if you take that logic to its extreme, and we filled the entire thing, that entire 5-inch space, with the best insulation on Earth, 5 inches of Pyrogel HPS, you'd have a very well insulated drum, and the incremental payback on that would be about 2.6 years. Now, everybody has their own economics. Everybody has their own thresholds for what constitutes an appropriate payback. But the option remains for anyone that you don't necessarily just have to meet your existing design for thermal insulation. You can, in fact, exceed it. And in many cases, the insulation will pay for itself in less than a year. We have a great example of that. This is a facility that had sort of a perfect science experiment. They had a 6-drum set insulated with mineral wool, and they put 2 new drums of the same size and shape in right next to the 6 existing ones. And the new drums were insulated with Pyrogel. This gave us sort of a control and a test. And on the test, the Pyrogel drums, after about a year in service, the process engineer there noted that the Pyrogel drum was running about 10 degrees warmer than the 6 older mineral wool drums. So there is the 1% yield that we all talk about. Based on that logic, this organization was far looking ahead enough to sort of turn that dial to the right. And the next 4-drum set that they installed, they did super insulate with 100 millimeters of Pyrogel, 4 inches of Pyrogel. That's an extraordinarily well insulated drum, but it was worth it because of the unit's higher production limits. My second case study is this idea of re-insulated while in service. So in this case, you know, you would ordinarily re-insulate a drum during sort of an extended turnaround. In this case, they didn't have the luxury. They were limping along with the insulation that they had. The turnaround was still several years away. And so we worked with them and the insulation contractor to develop a plan to do this while the drums were in service. Now, we're not doing it while it's coking, but during the cutting operations, we would essentially take a bay, say 10 feet tall, and all the way around the drum. We would demolish the insulation, take it all off, and then over the course of the next few cycles, re-insulate that bay and re-jacketing. Typically 2 to 3 cycles to do a bay on a drum. Then you move to the one just above it and the one just above that, and work your way up to the top of the drum. Now, this isn't something that you can really do on top heads or bottom cones. The bottom cones is not a particularly safe environment to be working in, and the top heads, you know, the access is difficult. But on the drum body itself, on the shell, doing live insulation is perfectly viable. We've done it here at a facility on the US Gulf Coast. We've also done one in Venezuela the same way. Once this unit was completed, the process engineer noticed that the coke thus produced had lower VOCs and was harder. And both of those are indications of higher liquid yields to the fractionators. Based on his back of the envelope, they figure that Pyrogel has increased their profits by $30,000 to $50,000 a month, and that's before they've even really trimmed the unit. Once they optimize furnace temperatures and flow rates, they expect to get even more. Finally, when you're at a point in your life cycle in which you're considering new drums or you're looking at a greenfield DCU, that opens up a couple of other possibilities. Certainly, you can super insulate. That's always on the table. But this raises another idea, and that's the idea of supersizing the drum diameter within the existing structure. So the structure basically mandates a certain diameter, an OD, of the insulation. If you use a thinner insulation profile, you can increase the ID of the drum basically within the same space. What would be the benefit of that? Well, there are a couple. One is that you can boost the internal volume and therefore the throughput by up to 8% just by skinning up the insulation. Also, by increasing the cross-sectional area, the internal cross-sectional area through which the vapor flows, it lowers the vapor velocity by up to 8%. Since dynamic pressure, and therefore the force which causes uplift on foam, drops by velocity squared, that 16% reduction in the risk of foam over, just by making the drum bigger and holding all else equal. And the only way you can do that is by having an extraordinarily thin insulation profile. The other thing that a thinner insulation on a new drum kind of project affords you is that it reduces the risk of mechanical damage as you lower pre-dressed drums through the structure, right? So you can insulate on the ground, which will always be more productive than insulating once erected. And you can do that by skinning up the insulation and reducing the risk of clashes as you drop it from one deck to the next. And I'll show you a case study in which we were able to do that. This is a refinery out in California where they replaced 6 drums into an existing structure. In this particular case, they were able to reduce the thickness of the existing insulation, which was 150 millimeters or 6 inches of mineral wool. They were able to skinny up that profile, reduce the drum diameter, the OD of the drum, by about 3 inches, and the result was basically flawlessly executed lift of the fully dressed drums into the structure. So with that, 5 case studies, I will go ahead and throw it open to some Q&A. Jump over to Slido here. Okay, so good question. So the typical insulation materials used in a delayed coker unit is, for the most part, it's mineral wool around the world, especially on the shells, on the drums themselves. Mineral wool board, blanket on the heads. On feed lines and overhead vapor lines, also mineral wool, although sometimes calcium silicate as well. Those are kind of the primary insulation materials that are out there right now. As I said, of the 120 some odd delayed coker units in the world now, about a third of them are starting to use Pyrogel HPS in particular. So those are kind of the big 3. As for water resistance, how does water resistance deteriorate with time and thermal cycles? It's a great question. So water repellency is in Pyrogel, and really in any product that claims to have some level of water resistance or hydrophobicity, it's necessarily a function of organic chemistry. So organic chemistry and high temperatures typically don't get along very well. And so what ends up happening is that on the fraction of the insulation that is nearest the drum, say the inner 50% of the overall thickness, the expectation of remaining water repellent goes away. So the inner half of Pyrogel basically loses that resistance. However, it is protected by the outer half. The outer 2 or 3 layers of material continues to protect, and that is the direction from which the liquid water comes, whether it's from rainfall or from overspray or cutting operations. So the system is still protected by the outer 50%, which basically retains its water repellency for the life of the system. Next question: you see any impact on foam front from better insulation? Right. So it is my understanding from talking to coking experts that one of the biggest predictors for having extended foam fronts is the temperature of the drum. A cool drum will tend to produce a taller foam front than a warm drum. So certainly keeping the drum warm will reduce that. As I mentioned before, if you are putting new drums into existing structures and opening up that cross-sectional area, reducing the velocity, that will also reduce the dynamic pressure or the head that's basically trying to lift that foam off of the surface of the coke itself. So those are two ways I think that insulation, in particular, a thinner, more efficient insulation, can impact the risk of foam overs. Next question: have you used Pyrogel on coke drum overhead lines? In fact, we have. We've actually done a fair number of those. They're kind of an interesting, what I would call a Goldilocks problem, in which you don't want them to be too hot nor too cold, so you're trying to balance it. Most people use some kind of quench to achieve that balance, but not everybody. So sometimes we're just putting on a little bit of insulation to try and hit that sweet spot on the temperature drop curve. But I would hazard to guess that we probably have 10 to 15 different units on which Pyrogel has been used on the overhead lines. And this last question is insulation, can it be used on the heater outlet lines? Yeah, so Pyrogel HPS, similar to mineral wool, similar to calcium silicate, has a 1200 degree or 650 Celsius maximum use temperature, although Pyrogel HPS is capable of a little bit more than that. So yes, Pyrogel HPS is perfectly comfortable for the outlet lines on a heater. Next question is a bird cage. And can we discuss bird cage applications, right? So there's the mechanical design around a coker, the insulation around a coker, is very, very important. Different than, say, just a run-of-the-mill distillation column in, say, a crude unit, where you don't have nearly the same amount of thermal cycling. The mechanical attachment of the insulation on a typical distillation column is fairly straightforward. On a coker unit, because there's so much movement, the typical approach of using breather springs is really less reliable. You know, those will work 3, 4, 5 times over the course of a column's life, but you can't expect them to actuate every day, do so reliably. So what some people have done is use what's called a bird cage. So on a bird cage design, there are a couple of different details here, but let's just say, for the sake of argument, that you can have a clean-sided structure with no clips or rings, or you can have a ringed structure, in which case the insulation is supported off of the body of the structure itself. In the most typical kind of bird cage, the structure is clean-sided, and over the top of it hangs essentially a dress or a skirt. It basically looks like a bird cage, which is why it's called. And so that floats up and down on the structure as the structure moves interior to that. Off of that bird cage is suspended typically a bunch of individual panels of insulation. So if you think about it, you know, you as a mechanical designer on a coke drum, you have two options. You attach the insulation to the drum, or you attach the insulation to the jacket. In a typical bird cage system, the insulation is attached to the jacketing, and the slipping or the sliding interface occurs between the inside face of the insulation and the drum itself. So there's a couple of companies out there that provide a bird cage system. One of the most experienced, I would say, is Insulate out of LaPorte, Texas. We've done lots of bird cage systems with them. They're very, very comfortable with using our materials. And in fact, the case study I showed earlier, in fact, two of the case studies that I showed earlier were done with bird cage system via Insulate. So it's a high reliability system. They don't all have to be done that way, and typically, say, Foster Wheeler units, now Wood Group, are not typically done with a bird cage, but you know, it is a viable option, and it's a very attractive one. What is the more compelling business case, energy savings or yield improvement for the client? Yeah, good question. It is almost always yield. It is a fact of life in the insulation business that energy is valuable, but it's not that valuable. It doesn't really add up to much of a savings if all you care about is the BTUs. BTUs are not that expensive in a refining environment. The business case for yield improvement, however, is typically going to be 15 to 30 times more compelling. So for example, if you wanted to sell your management on the idea of better insulation, and you ran through the energy calculations and it said the payback on it is 20 years, if you did the same thing on yield, the payback on that would be typically about 1 year, right? So when you go through the math, I usually count both, but the yield improvement argument is far, far more powerful than the energy saving argument. Next question, examples of where Pyrogel is used on delayed cokers. This is, if you can see my screen, I have, no, you cannot see my screen. That's all right. We have a list, a reference list that I can provide after the fact, Rakesh, where we can show where we've been used. In many cases, it is for partial applications, again, feed lines, top heads, bottom cones. And then also we have a series of references for doing full drum installs. I think at last count we have 38 or 40 full drum installs completed, and a dozen more that are basically in process right now. So we can follow up after the fact with full reference list. Next question, when replacing drums on a unit, what savings in time and money have you seen when pre-insulated versus standard insulation? Right. So that's a good question. So pre-insulation can mean a couple of different things. Typically, pre-insulation means when the drum is laying down on its side next to the unit prior to the lift, right? And when you can do that work, number one, you're not using engineered scaffold, right? You're only having to scaffold up to, say, 10 meters above grade. And that's a cheaper scaffolding to install. And just any time that you can dress equipment horizontally rather than vertically, it's going to be cheaper and faster, especially in a scenario such as in a coker where it's completely surrounded by structure. Yeah, that makes the scaffolding a little bit more convenient, but it's a very constrained and work environment. So, you know, being able to do it horizontally is probably twice as fast as being able to do it vertically. The other sort of scenario that comes up and that we've done, in fact, is that when you pre-insulate, you don't necessarily have to pre-insulate in the unit or even on site or even in the same country. We've done jobs in which the insulation work was actually done in the fabrication yard where the coke drum was built. Now that does a couple of things. Number one, it takes the insulation really off the critical path, right? It's done somewhere else. And typically in those places, well, often in those places, you have a different kind of cost of labor. So you can take advantage of that for the same reason that you may have gone there to fabricate your drums. You might want to consider fabricating your insulation or installing your insulation there as well. Now, what we have learned is that it's not a no-brainer. You have to go to extra lengths to protect the drums in transit because equipment that is installed vertically is installed in such a way that all of the watersheds work to, shed water off of the drum when it's in a vertical configuration. When you turn it 90 degrees and lay it on its side, your watersheds are all pointing in the wrong direction. And so you can't necessarily rely on your sheet metal to keep everything dry, especially after it spends 6 weeks on the water. So what we've learned is you have to package the drum. If you're going to pre-insulate in the yard or in another country prior to loading it onto a barge, you have to package the drum and basically shrink wrap in order to protect it during transit. But it is a perfectly viable option, and we've shown that it can be done. Next question, is it a cost-effective to use Pyrogel to insulate valves and odd-shaped process equipment requiring multiple pads? Yeah, so that's a great question. So we love removable pads. You know, typically your removable pads are either filled with ceramic fiber or needle glass. And so Pyrogel is going to go in at generally 50 or 60 or 70% thinner. So that's a convenience. Now that pad is going to cost more money to install, but you're going to be able to use it for a lot longer, because every removable pad that you have will end its life in a crumpled up ball on the ground, because it will be left out, it's going to get wet, it's going to get heavy, it won't be put back on, or when it does get put back on, because it's wet and heavy, it doesn't fit properly. So this is a pretty typical end-of-life scenario for removable pads, and it's an end-of-life scenario that Pyrogel simply does not experience. So I would argue that that is one of our favorite things to use, is Pyrogel inside of a removable pad. You're going to spend a little bit more for it up front, but you will have it for much, much longer. Next question, how Pyrogel installation is performed related to surface preparation and painting before the insulation is applied? So good question. You know, the materials that we produce are largely agnostic to the kinds of coating systems that you use underneath, right? So they don't really interact meaningfully. So whatever your coating spec is, we wouldn't necessarily ask for any changes around that, because you're using Pyrogel. What I would say is that there are scenarios in which a coating application is difficult, if not impossible, particularly for stuff that's being done in the field, where you are doing some sort of emergency weld repairs, and doing things in which surface prep and painting may not be viable within sort of a confined time schedule. Now, we don't recommend not coating your surfaces before you insulate, but if you are in a situation in which that's the only thing that you can do, I would argue that Pyrogel is the best option for you, because without water, corrosion cannot happen. And Pyrogel does the best job of anything out there of keeping the water off of the pipe. Next question. I understand XTE mainly used in DCU. You have a new product, HPS. Would you please explain the difference between XTE and HPS? Right. So good question. XTE is kind of our sort of flagship hot insulation product, Pyrogel XTE. HPS is just a little bit better, right? So HPS is has a slightly different fiber, so basically it lasts longer, and it's more reusable even at temperatures up to 1200 degrees Fahrenheit. That was one of the requirements that we gave to our R&D folks, is that we want to be able to reuse this material over and over again. And one of the things that limits that is the quality of the fiber, and HPS just has a slightly higher quality fiber in it. The other thing that HPS does is it has a better thermal conductivity, above 300 degrees Celsius. At room temperature, the materials are basically the same, and in a dark room, you wouldn't be able to tell the difference. But at 850 degrees Fahrenheit, or 900 degrees Fahrenheit, or 500 degrees Celsius, HPS is considerably more efficient, and enough so that you can generally peel off one layer of Pyrogel with an HPS system. So it will generally be thinner than the XTE. So it is thinner and tougher in this kind of surface. Next question. Could you share the time requirement for a typical 8x40 drum Is it possible to change online completely without any downtime? If so, what is the duration? Right. Okay. So, Santosh, we can probably take that one offline, what the time requirement would be for an 8x40 drum. It is possible to change online, except for the bottom cone and the top head. That you can't do online. That you have to do during a shutdown, turnaround. But the body of the drum, which is 80% of the surface area, you can do online, typically during the cutting cycle. What is the duration? The way you would organize that is you would operate one ring at a time. And as you insulate each ring, you de-insulate a ring and then you insulate and re-jacket a ring. Typically that is going to take somewhere between 2 and 4 cycles, depending on what your process time is. So if you can kind of baseline 3 cycles per ring, and if you have 6 rings per drum, then you're going to need 18 cycles to basically redress it from top to bottom. This is going to take a lot of coordination with your installation contractor, but it certainly is possible to do. And so we could work with you on that. I look forward to talking to you offline. Okay, last question here. Seems clear for refiners. See benefits of Pyrogel in existing units. Seems more effective to consider this technology during project design. Do you have experience of engineering companies that are using Pyrogel as technical requirement? Yeah, fantastic question. So yes. So as I mentioned before, Foster Wheeler, now Wood Group, we work with a lot of those kinds of process licenses, Foster Wheeler process licenses. They have since, I'm going to say 2013, specified Pyrogel on all of their top heads and bottom cones. Top heads because that's the area that typically gets destroyed by water. Bottom cones because that's the area where they have the most mechanical clash with the delta valves. So Foster Wheeler certainly would. I have to get out of that habit. Wood Group is certainly very comfortable in using Pyrogel on their drums. Bechtel, the owner of the old ConocoPhillips process license, has done several drums with Pyrogel as well from the ground up using Pyrogel. We are, I think, I would say in discussion with both Loomis and EIL for their process licensors. We have certainly done maintenance work in those facilities using Loomis and EIL technology, and so we're kind of slowly working through the process of getting it introduced at the very beginning. Certainly ExxonMobil, their process, ExxonMobil has been one of the biggest believers in Pyrogel technology going back 15 years or more. So we end up getting a lot of DCU work through ExxonMobil, and so they're certainly very comfortable with that as well. So I think that covers most of the big licensors. So with that, fantastic questions. Appreciate it, everyone. Becky, maybe I can turn it back over to you.
John, thank you so much for that great presentation. I will be sending a wrap-up email that will contain John's email address. If you have any questions or would like to reach out to him specifically, please do so. I do want to point out that there are a few more webinars coming up in the next few weeks that might be of interest to you. Please find all the details and the registration links on our website. We are also holding REFCOM Global. It's a delayed coking conference and exhibition the week of November 2nd through 6th. We invite you all to attend. The REFCOM Global webpage has all of the details. Please check there for updates. We are offering 2 free passes to every DCU site globally to REFCOM Global. This is an all-access pass to everything during the week, the conference and exhibition. I have heard from about 25 sites, so please contact me to get your free pass. And with that, I'd like to thank you all for joining us today. It looks like we're ending a little bit early. We do appreciate your attendance, and we hope that you will join us again for a future eRefCom webinar. Have a wonderful week.